Let's take a look at a two-dimensional collision. Actually, let's be more specific, a perfectly elastic collision. I'm going to solve this two different ways. So this video, I'm solving it sort of the straightforward method, and then I'm going to shift reference frames for the second method. So let's run through it. So if I have a 5 kilogram mass heading to the right at 2 meters per second, heading towards it is a 3 kilogram mass heading to the left at 4 meters per second. They're going to collide, so this is the before picture. Afterwards, they're going to hit each other and go careening off. So if this is the line upon which they were originally traveling, after the collision, the 5 kilogram mass is traveling this way at some speed c, and the 3 kilogram mass will be traveling this way at some speed of d. So it's a collision. So momentum is conserved, but I have two dimensions here. So if we set up I hat, j hat, it'll be conserved in the I hat direction and the j hat direction. So in the I hat direction, P initial equals P final. And so we end up with 10 plus negative 12 equal to negative 2 kilogram meters per second. And so our equation is, this is initial. So I have negative 2 is equal to 5. Let's give an angle. This angle right here I do need to give to you, and I'm going to make it 36.869897645 degrees. In other words, I'm picking that angle just so that there's less issue with rounding. The cosine of that angle is 0.8. and the sine of that angle is 0.6, just to make the math a little bit easier. And this is going at some angle theta. So negative 2 is equal to 5 times c times the cosine of this angle, which is 0.8, plus negative, since it's going in the negative direction here, negative 3 times d times the cosine of theta. In the j direction, I have 0 initial momentum in the j direction, so afterwards I have to have 0. And so this becomes 5c times the sine of that angle, which is 0.6, minus, because it's down, 3d sine of theta. And then because it's perfectly elastic collision, we do have kinetic energy initial equals kinetic energy final. Those are capital K's. So I have 1/2 times 5 times 2 squared plus 1/2 times 3 times 4 squared equals 1/2 times 5 times c squared plus 1/2 times 3 times d squared. And right off the bat, we can simplify this best by multiplying the whole thing by 2. It makes life just a little bit simpler. And while we are here, the initial energy, or at least twice the initial energy, because I multiplied by 2, the initial kinetic energy becomes 20 plus 48, or 68. So my three equations, negative 2 is equal to, that becomes 4c minus 3d cosine theta. I have, let's go ahead and bring this over to the other side. And so 5 times 0.6 is 3, so I have 3c is equal to 3d sine theta. And my final equation is I have 68 is equal to 5c squared plus 3d squared. So those are my three equations. I have three unknowns, definitely solvable. So again, this is conservation of momentum equation in the I direction, conservation of momentum in the j direction, and then conservation of kinetic energy because it's perfectly elastic. All right, so from this second equation right here, I can obviously divide by 3, get rid of that, so I have something for the value of c. And so if I plug that into each of these, I have negative 2 equals 4 times d sine theta minus 3d cosine theta. And then, so that's combining those two. Combining those two, I have 68 is equal to 5 times d sine theta squared plus 3d squared. I can now solve for d in this equation and plug into that one, because now I'm down to 2 unknowns. So from this equation right here, I have negative 2 is equal to d times 4 sine theta minus 3 cosine theta. And so d becomes negative 2 divided by 4 sine theta minus 3 cosine theta. And d squared, because we're going to need it, it's going to be 4 over 4 sine theta minus 3 cosine theta, that denominator squared. From this equation right here, we'd have 68 is equal to 5 d squared sine squared theta plus 3d squared. Factoring the d squared out on the right-hand side, I have 5 sine squared theta plus 3. So d squared is equal to 68 over 5 sine squared theta plus 3. So I have two values of d squared, and now I can equate them to each other. And so I end up with 68 times 4 sine theta minus 3 cosine theta, that quantity squared, is equal to 4 times 5 sine squared theta plus 3. 4 goes into 68, so we can simplify it. So if that goes into 68 17 times. And now let's just multiply some stuff out. So because theta is the only angle I'm dealing with here, I'm just going to drop writing theta. So when I write sine, it really means sine of theta. So this becomes 17 times 16 sine squared minus 24 sine cosine plus 9 cosine squared is equal to 5 sine squared plus 3. Distributing the 17, I get 272 sine squared minus 408 sine cosine plus 153 cosine squared is equal to 5 sine squared plus 3. Now I've got the sine and cosine mixed in together here, plus a cosine squared there. So I need to get it in terms of the same trig function. And so I know that this is 1 minus sine squared. So I'm going to bring this over to the other side, distribute that, and bring this over to here. And so I have 272 sine squared plus 153 minus 153 sine squared minus 5 sine squared minus 3 equals 408 sine cosine. And let's just put those side by side again, just to make sure that they're looking right. So we bring this, that stays the same. This one we brought over to the other side, so that's why that's positive. The 153 times 1, 153 times sine squared, and then brought this over to the left side, so that's why that's negative. Brought the 3 over, that's why that's negative. All right. Let's combine like terms. I got sine squared, and sine squared, so 272 minus 153 minus 5, so that's 272 minus 158. So I have 114 sine squared plus 150, combining those two, is equal to 408 sine times cosine of theta. I can divide by 6 to simplify this down a little bit. So I have 19 sine squared. So again, divide by 6. 19 sine squared plus 25 is equal to 68 sine times cosine. Now I need to get rid of this coupling here, so I'm going to square both sides, which doesn't immediately get rid of the coupling, but then I'll have a cosine squared, which I can convert to a sine squared. And so I have 361 sine to the 4th plus 950 sine squared plus 625 is equal to 4,624 sine squared cosine squared. That's 1 minus sine squared right there for cosine. And so now I have this is equal to 4624 sine squared minus 4624 sine to the fourth equal to all of this. Basically, I'm dealing with a quadratic here, even though it's a fourth power, but I'm going to look at it as a quadratic. So I'm going to get it in terms of treat sine squared as an entity. And so I'm going to get everything over onto the left-hand side. So I've got this when I add to that. So I have 4,985 sine to the fourth power minus, because I'm going to subtract this from both sides, so I'll end up with a negative. So negative 3,674 sine squared plus 625 equals 0. And so therefore sine squared of theta is equal to 3674 plus or minus the square root of 3674 squared minus 4 times 4,985 times 625. I am assuming that you know how to do the quadratic formula. Divided by 2 times 4,985. If you're not quite sure how I got from here to here, just look up the quadratic formula again. I'm treating sort of that as x, and so that would be x squared, and so I'm just solving for x. So working through the math, which fortunately for you I've already done, so that's either equal to 0.470584 or 0.2664219. So that would translate into, again, that is sine squared theta. So sine of theta would be 0.68599 or 0.516164.8 and so on, which would then translate into theta is equal to 43.31 degrees or 31.08 degrees. So let's take a look at the second solution. So I do have formulas here. I have a formula for d right there in terms of theta. So d is equal to, just rewriting that formula, 4 sine theta minus 3 cosine theta. And so if I plug in the d's, I get negative 2 over negative 0.5048, which is 3.96 meters per second. My formula for c, I know that c is equal to d sine theta. And so this would be 2.045 meters per second. Now, if I use the first angle, this again is theta is 31.08 degrees. Now, if I'd chosen theta is equal to 43.31 degrees, notice what happens to d, and I have d is equal to negative 2 over 4 sine of that angle minus 3 times the cosine of that angle. And I did not write it down, so let me go ahead and calculate that again. This would be negative 2 over 0.5608223, which is negative 3.56619 meters per second. Now, what that would mean is that d is going in the opposite direction. So if we go back to the original drawing, if d is negative, that means that d is going in the opposite of what we had said. So this angle right here would be the 43.31 degrees, and d would be heading in that direction, and that's just impossible. You can't have two things colliding like this and then both of them go off in that direction. That would violate conservation of momentum. So if you're thinking of, wait, how does that violate that? I've done that on a pool table. Recognize there's another factor involved, and that this is just these two objects. This is a closed system here. If you bring in the pool table, you now potentially have an open system if all you're looking at are the two pool balls. Also, the masses wouldn't be that far apart. So our final answer, so this is not the answer. So the final answer is that 5 kilogram mass is shooting off at our approximately 37-degree angle at a speed of 2.045 meters per second, and the 3 kilogram mass is shooting off at an angle of 31.08 degrees and 3.96 meters per second. Now we're going to solve this again slightly differently. Just math is put into a different spot, but we're going to shift reference frames, and anyway, that's for the next video.